Okay, I'm going to try to give a brief introduction of the fundamental concepts underlying DTI. The challenge here is really that there is no real short way to explain all the concepts underlying DTI that's also brief and complete, but I'll do my best. You can't really understand what your DTI measurements really show unless you know what you're measuring. It's really important to know what you're measuring, to know what you can trust, what you can't trust, what are the limitations. So I'm going to try to give a brief explanation of these, the most important, I think, core concepts, covering where the MRI signal comes from, how we use the signal to get an image, how we can also take that same signal and weight it and relate it to water self-diffusion, how diffusion-weighted imaging, DWI, is done, how diffusion tensor imaging, DTI, is done based on multiple DWI, right? And how fiber tracking can be done using DTI data. So I've also introduced a couple of terms here, DWI, DTI, and fiber tracking. Not interchangeable terms at all, right? Very different things. So I need to explain the core concepts of the imaging sequence piece by piece and then put them together. Hopefully by the end then you'll be able to understand this diagram of a spin echo sequence, and I'll be able to show you then how we're going to add magnetic field gradients to put diffusion, weighting, and coding into the MR signal as well. This diagram shows some core concepts that I'm going to explain in more detail. First of all, we're detecting hydrogen nuclei. They're mostly in the body in water and lipids. Hydrogen nuclei, protons, have magnetic properties, so that when we put them in a strong magnetic field of our MRI system, the tissues actually become weakly magnetized. Not enough to affect physiology, but enough we can detect it. At equilibrium, the magnetization is parallel to our main magnetic field of the MR system that we call B0. And in that state, we can't detect anything. We need to disturb the magnetization, tip it away from alignment with B0. And we use a radio frequency pulse, another magnetic field, to do that. Once it's tipped away from alignment, it'll precess around in a cone like a gyroscope moves. That makes a time-varying magnetic field that we can detect with a coil. That's our MR signal we're going to detect. Through this whole process, as soon as the system is not in equilibrium, the processes of relaxation are going on. That's driven by random thermal motion of protons. They're exchanging energy, they're losing energy into thermal energy. And relaxation actually tells us something about the chemical environment of the water. So these are the steps we're going to cover. So the reason we use hydrogen for MRI is that hydrogen nuclei are incredibly abundant, for one thing, in the body, in water and lipids. And they're one of a number of atomic nuclei that have magnetic properties. They have north and south poles. They have a magnetic field around them. And so we can use that magnetization. We put them in a strong magnetic field of our MRI system, and we can orient the magnetic field like a compass needle points north. We can create a net magnetization. When we average over a tiny volume of tissue, which is a huge number of protons in there, it creates a net magnetization, a net magnetic moment per unit volume. Now, the protons also have the property of spin. They have angular momentum, like a spinning top, like a gyroscope. When they're not aligned with the magnetic field, the force trying to pull them into alignment actually makes them precess or wobble around. We're going to use that property of its precession and its angular momentum to get our time-varying magnetic field and get our MR signal. I want to quickly show a few core physics ideas that are going to keep coming up. This is a gyroscope. You can see when it's not spinning, you let it go, it just falls like you would expect. But when you make it spin, when you give it angular momentum, like I mentioned our protons have, then it has interesting properties. Here you can see, because of its angular momentum, well, it actually objects resist changing momentum. So here gravity is trying to pull it down, and because it's spinning, instead of falling, it actually precesses around in a circle like this. And so this is basically what our protons are going to do in our magnetic field as well. The magnetic field is trying to pull them into alignment, and when it's not in alignment, instead of just snapping into alignment, they precess around in a cone. And with our protons, we can easily predict the exact speed they're going to precess at. So we know what kind of rate of wobble we're looking for. Here's another key idea that comes up over and over again, and it's a fundamental part of the design of the MRI system. When you put an electric current through a loop of wire, or any wire, it makes a magnetic field around it. The magnetic field through a loop is actually directed through the center of the loop. So here he's put some iron filings between two plates of plastic, and they're in oil so they can move around, and they're just randomly oriented right now. But when he puts the current through the wire, the magnetic field that is created will actually make the iron filings align, and you can see the direction of the magnetic field around the wires and through the center of this loop. And there it is, and that's the basic idea behind our MRI system. Huge current through a big loop of wire. Now we use almost the same idea for receiving the signal. Here is showing if you put a magnet in and out of a loop of wire, it induces a current in the wire. And you can see if he puts the magnet and just leaves it there, the magnet's not moving, no current induced. Current's only induced when the magnet's moving. It's only a time-varying magnetic field that induces a current. The faster the magnetic field changes, the bigger the current that's induced. That's what we're going to use to detect our precessing magnetization. And now, just in case you've never played with magnets, just so you know, magnets have a north and south pole, and they'll align with each other a certain way. North poles on two magnets repel each other, but north and south poles attract each other. The magnets will tend to align a certain way in a magnetic field, and they'll attract each other in a certain way. Now, hopefully if you didn't already understand it, some of the shape of the MR system and the coils and everything we use and what they do is now starting to make more sense. Now, I want to represent here a single magnetic moment vector in our magnetic field at equilibrium, but you actually can't see it. It's drawn in red. And what's shown in green here is the direction of our magnetic field B0. So what this is representing is just the equilibrium state. A magnetization vector is aligned with B0. Nothing's happening. There's no time-varying magnetic field. Okay, there's nothing to detect. Now this is representing if we had the magnetization vector in red, it was actually at an angle to B0. Here it is precessing around, as I mentioned before. This is our time-varying magnetic field. Okay, but we want to get a signal from a whole bunch of different locations in the body at the same time to be able to create an image. So first we need to rotate our magnetization away from alignment with B0 so that we can get it to precess around B0 and give us a signal we can detect. Okay, it's not practical to rotate B0. It's a huge magnetic field, 3 Tesla, 30,000 Gauss. Well, we can add a small magnetic field to it, transverse to it, so the sum is in a different direction. We can't add a huge field. We can't make another 3 Tesla field. That's not practical either. We can add just a tiny little field, like 1 Gauss. And so here we're showing the original magnetization in red. Now it's precessing around a total B field that is ever so slightly at an angle from the original B0. So it's precessing in a small cone, right? That doesn't give us much signal. It doesn't help much. But if we make the added field, the small transverse field, rotate at the same speed as the magnetization is precessing, then we have like a wobbling B field that the magnetization is precessing. The magnetization in red is precessing around a moving target in effect. And the effect accumulates and accumulates. This is the resonance effect. Even though it's a tiny effect, when it's at the right frequency, it has a huge effect on the magnetization. And we can actually rotate the magnetization in red through any angle we want away from B0. Right? As long as we have this additional rotating magnetic field turned on, this is actually our radio frequency pulse, our RF pulse. Okay? As long as we have it turned on, the magnetization keeps precessing around the sum of the two fields, and we can rotate it away from B0. Then when we have it rotated through the angle we want from B0, we just shut off our added magnetic field. We shut off our RF pulse. So we can actually deliver our magnetization through basically any angle we want away from B0. So this is a good time to introduce the concept of magnetic field gradients. So far I've only shown it as though all the magnetic moment vectors everywhere in the tissues precess at the same speed. The precession speed depends on the magnetic field strength. If you double B0, you double the precession speed. And we're not going to do that. We're just going to add a small disturbance to the magnetic field. We're going to add yet another magnetic field. This is our gradient field, and it adds or subtracts from B0. But we make it so it's a linear gradient. That is, B0 field will now depend on position in a slight way. Here I've shown this as though the gradient is in the x direction. So on the right side of the body, B0 is a little bit lower. On the left side of the body, B0 is a little bit higher. And as I've shown here, it is a small disturbance, but it makes the precession frequencies depend on position in right to left here. Now imagine if we applied an RF pulse with our rotating magnetization at a certain speed, it would affect a certain range of the x-axis. Everywhere in the y-z directions is the same, but only on the x-axis, only a certain range is affected. The rotating magnetization doesn't have to match the precession speed exactly. There's a small window where it has an effect. So we end up having an effect just on a certain slice. If we put a gradient in the x direction, if that is right, left, anterior, posterior, and head, foot, that'd be like a sagittal slice. Or that is our first spatial dimension for defining our images. We're going to do a RF pulse, and we're going to make it spatially selective by putting it on during a gradient. It's also important to mention that gradients will come up over and over again later on, because gradients are what we use to encode our diffusion sensitivity into our signal. So these are going to be of critical importance in the parts that are going to follow. Okay, we've covered a bunch of these ideas. We've got the equilibrium magnetization, how we're going to disturb it, what it does, how it processes around when it's not at equilibrium, even how we're going to add gradients and make its precession speed depend on position to give us some spatial information. I haven't talked yet about relaxation. This is the process how it originally gets into equilibrium when we put our body in the magnet, and also after we've disturbed it, how it gets back to equilibrium so that we can do this whole process again and get more signal. Now, the processes of relaxation and diffusion are actually also related, and this is quite important for understanding diffusion-weighted imaging. Look at the environment the protons are moving around in. And they interact with each other just like two magnets do. And they're moving around under random thermal motion, but their motion depends a lot on if they're in free water, if they're interacting with solutes, interacting with large proteins. That mobility strongly influences how much they can interact with each other, how much they can exchange energy with each other, and how energy can be exchanged between them, and also into what we call the thermal lattice. That is, energy is, because of interactions, energy gets exchanged into thermal energy. You can imagine two protons coming near each other, repelling each other. One moves off more quickly by having lost magnetic energy. So this relaxation process converts magnetic energy into thermal energy. That's where the energy goes as the system settles back into a lower energy state at equilibrium. So the mobility has a huge effect. Of course, mobility is what we're looking at for diffusion. How do these hydrogen nuclei move around? And of course, it's determined by the environment they're in. So for relaxation, it actually gives us some important physiological information. So now let's look at it in terms of the MR signal. Now I'm showing separately the longitudinal and transverse components. Here as though we're tipping the magnetization with an RF pulse. Okay. Now some books will describe relaxation as though it's tipping back like this, and that's actually not true at all. It's actually a bad idea to think of it that way. We need to think of this in terms of the fact that there are billions upon trillions of independent hydrogen nuclei moving around in this water environment, all contributing to the signal. When we tip it with an RF pulse, all the protons are affected the same way, so they move in a coherent way, and our net magnetization looks like you can think of it as one thing tipping. When they're all acting independently, though, they don't act in a coherent way. The transverse component decays much more quickly to its equilibrium value of 0 than the longitudinal component grows back to its equilibrium value. Remember, the transverse component is the one we're detecting to give our MR signal. Okay, so it's very important, this distinction, the transverse component, the longitudinal component. The transverse component, which we characterize at the time T2, decays about 10 times faster typically than the longitudinal component grows with its characteristic time of T1. Right? So we need to consider transverse and longitudinal components of relaxation separately. Okay, so now we want to put all these ideas together and show how we're going to tip the magnetization, get a signal with the relaxation time weighting and with spatial information, and then we're going to add the diffusion weighting. Okay, we're going to start with our signal at equilibrium. Here I've drawn a bunch of different magnetization vectors as though they're from a bunch of teeny little volumes. Imagine just a span of a few millimeters. Then we tip them with an RF pulse. They all process together. Okay, now I've drawn them as though they're all the same length here. Now in reality they might have different signal strengths because they might have different numbers of protons. But here they're all showing processing together. Now we need to add a magnetic field gradient because we need to have spatial information. Okay, now they're drawn as though they have different signal strength, as more realistic, as though they have different number of protons. Different types of tissues may be given different signals from different locations. Okay, now the signal's shown with a gradient on. All of these small magnetic moment vectors started in the same direction right after the RF pulse. But now you can see they're all processing at different speeds because they have different magnetic fields. There's a gradient on. And you can see right away it doesn't take very long for them to get out of phase. Right? The ones at the far left are processing faster than the ones on the right, and they get all out of phase. And in reality, this will cause the total signal induced in the coil to quickly drop to a very small value, actually drop to 0. So this is a problem. We need to get the signal with a magnetic field gradient on, but they quickly get out of phase, so we start to lose signal. So in order to get a strong signal while we have a gradient on, we need to do another step. We're going to need to create an echo of the signal, it's called. Okay, I'm showing this again, but this time I'm only showing the transverse component of the magnetization, because this is the component we actually really care about the most. So this is the component of magnetization that induces a current in our coil. This is what relates to our signal that we're going to measure. Okay, so one way to create an echo is to actually reverse the gradient that is causing them to dephase in the first place. We need a gradient on so that the protons at different positions process at different speeds, and we can tell where they're coming from by the frequency they induce in our receiver coil, in our signal. But we can, partway through this, reverse the gradient direction, bring them back into phase to make a bigger signal, and still acquire a signal with a gradient on. So right around now, reverse the gradient. Probably didn't notice it. The ones on the left were going faster than the ones on the right. Now it's reversed. Now the ones on the right are going faster. And so they're going to start to catch back up to where they were. Right at around 0.4 on the axis it's showing there, they're going to come back around to all point in the same direction. And so the signal they all produce will sum up, and we'll get a stronger signal in our receiver coil. So we could be acquiring the signal this whole time, and we'd see the signal build and build and build till it reaches a peak, we call the echo, and then it'll continue then to get smaller and smaller and move out of phase again. And this is called a gradient echo because we've done it by reversing the gradient. So it's a way of getting a stronger signal while we still have a gradient on, giving us the spatial information. Of course, while this is all happening, relaxation processes are always also going on, and so the echo is never as big as the original signal, but it's a stronger signal than we could acquire if we didn't do an echo. Another important thing to note from this diagram here is keep in mind the actual precession speed is around 127 million times a second at 3 Tesla. So this is a really kind of artificial demonstration. The precession speeds are much faster. And the times we would normally use from the time we do our RF excitation pulse to the time when we create an echo might be around 30 milliseconds. So I haven't really shown things in scale in terms of time. Now another way of producing an echo is instead to do a spin echo. Now we don't reverse the gradient. Instead what we do is we apply a second RF pulse. On this scale it'll be around about 0.2 on the horizontal axis as our time axis. We'll apply a 180 degree RF pulse. That'll be to flip all the magnetization everywhere 180 degrees around the x-axis. So you might not notice it is coming up. They'll suddenly flip. There. We didn't reverse the gradient. Okay, so the ones that are on the left that were going faster are still going faster, but the 180 degree pulse had the effect of basically inverting the effect of what happened before the 180 pulse. Okay, so even though they're all going the same speed, they'll still start to come back into phase and create an echo. This time it's a spin echo. Critical difference between a gradient echo and a spin echo is that a gradient echo is T2 star weighted, spin echo is T2 weighted. T2 star has all the additional effects of spatial field inhomogeneities. In the brain, T2 star is around, say, 30 milliseconds, whereas T2 is closer to 90 milliseconds. So with T2, we have a longer time to create a stronger signal. And there are advantages and disadvantages to gradient echo and spin echo that I won't get into here. Okay, finally, we've got our spin echo. Here it's shown again. Now hopefully it'll make more sense to you. We've got our initial 90 degree RF pulse. We tip it 90 degrees, get the most signal we can. Okay, we wait a little bit of time, let things actually dephase. We actually put some spatial encoding gradients on that I didn't really explain. Then we do a 180 degree RF pulse. Flip the spins. Okay, so we can create a spin echo. Again, we put on spatial encoding gradients that I didn't really explain. But the idea is, again, we need gradients on while we're acquiring a signal so that we can tell from the precession speed of the spins where they're coming from. Okay, we need to acquire the data with a whole bunch of different combinations of spatial encoding in different directions in order to build up the two-dimensional information about where all the signals are coming from in our 2D plane. And remember, we've already defined a slice with our spatially selective RF pulse. So I haven't gone into the spatial encoding part. But now, in the spin echo, we're going to add gradients. Now we're going to make our signal depend on if the water is moving around under random self-diffusion through the water. Okay, now so check out what happens if we do the same thing. Simulate our spin echo, but now we allow the spins to be doing a random walk, simulating random diffusion. Of course, it's kind of exaggerated, and I'm only summing the signal from 6 kind of theoretical places, but you get the idea. Because they're moving around, they're not in the same magnetic field all the time, right? The field they're in, because of the gradient, depends on their position. The position's changing. So the way that the signal will come in and out of phase, and the way we're going to create a spin echo, okay, or a gradient echo, but in this case I'm showing a spin echo, okay, will depend on how they've moved around. If they weren't moving, everything comes nicely back into phase, we produce a nice spin echo. Because of their diffusion, the refocusing will be imperfect. We'll have less signal. And so our signal is attenuated in relation to their diffusion. The peak of our echo is actually coming up around 0.4 on that horizontal. If you go back and compare it with the previous one where they weren't moving, hopefully you'll be able to see that it's a little bit attenuated. So now we need to do this in real life with actual water diffusion distances. So we're going to need to put on some pretty strong gradients. Also, we're going to need to allow quite a bit of time for these to diffuse around in one gradient, then do our 180, and then put a second gradient on and let them diffuse around in that, so that if everything was perfectly still, the two gradients would cancel each other out. But when the water is diffusing around, the gradients don't cancel out, then our signal is weighted according to diffusion. And it's important to note it's attenuated in relation to the diffusion rate only along our gradient direction. We could put a gradient in a different direction and see the effect of diffusion in another direction as well. So now we have all the ideas together. Here we've got our spin echo sequence, and this is showing with the gradients added. Now this is as though we're putting diffusion weighting along the axis here that we've labeled frequency encoding direction. And that could be left, right in the body, it could be anterior, posterior, it could be head, foot. We can put these gradients in any direction we want. We can put them along multiple axes at the same time. The gradients are defined along X, Y, and Z axes, but we can put gradient fields along multiple axes at the same time to create a net gradient in any direction we want. And so you can see in the diagram where the gradient, where the diffusion weighting gradients will go before and after the 180 pulse. And here I'm just showing the important features, the magnitude of the gradient, that is, how strong is this gradient. That'll have a direct effect on how strongly we encode diffusion sensitivity under our signal. So the magnitude of the gradient here is G. And then other factors that are important are how long we allow the water to diffuse around while we have our gradients imposed. The longer we let the water diffuse in the presence of gradients, then the more sensitivity we're going to have to diffusion. Here showing the timing between the onsets of the two gradients is capital delta, the Greek delta. So this time interval is important in the diffusion sensitivity. And then another really important factor is the duration of each of these gradients, which we labeled lowercase delta. So these three factors are going to play a role in calculating our diffusion sensitivity. Now, to get the most sensitivity to diffusion, we're going to want these gradients to be as strong as possible and really on for as long as possible. We have to take into consideration another important factor is that the longer we put these gradients on, then the longer our echo time has to be. Remember, all this is happening while we also have relaxation occurring. And so our signal is also T2 weighted. If we try to put our diffusion encoding gradients on for too long, just the transverse relaxation will make it lose a lot of signal. We lose a lot of sensitivity. So we need to balance how strong our diffusion weighting is with how long it's going to take to impose that diffusion weighting. So finally, we're going to base our calculations on this equation developed by Einstein, where he worked out that the distance you'd expect objects to move on average when they're undergoing random diffusion is given by this equation here. Square root of 2d delta t. Delta t is the time interval over which you let them move under random diffusion. D is our diffusion constant. People have also worked out the effective B value. This is the amount of diffusion weighting we have in our MR signal. Basically, it's a weighting factor for how we can calculate how much our signal will be attenuated by diffusion. So in this equation is the gyromagnetic ratio, gamma. This is a constant for protons. G is our gradient strength, which we've chosen. Lowercase and uppercase delta, these are values, timing values that we've chosen. So all these values are things we've chosen. We set the value of B. And this is what we refer to always as our B value. This is an important parameter that we'll set when we're requiring our DTI data. And it typically has values in the range of 0 to 5,000 seconds per millimeter squared. This is a typical units for B value, seconds per millimeter squared. You might see it written in other values, but this is fairly typical. This is the equation for our signal strength, S. This is what we actually measure. Basically, it's in our voxel, in a diffusion weighted image, the image intensity, the voxel value. S0 is the value we would have with no diffusion weighting on. That is, if we set B to 0. And so this value is going to be a factor of how many protons are there given a signal, the proton density, as well as factors like T2 weighting and anything else. On top of that is imposed the effective diffusion weighting. And it's an exponential function, e to the minus b times d. So our b value, again, we've set d value is what we're trying to measure. So we're going to measure S at a bunch of different values of B we set, and then we're going to calculate S0 and D. Given that the diffusion rate in the brain is in the ballpark of 1 times 10 to the minus 3 millimeters squared per second, you'll often see B values chosen to be in the range of 1,000 seconds per millimeter squared. Because then this gives B times D is about equal to 1. This is around the range that will give us the best sensitivity to changes in our diffusion rate, D. Okay, if you set the B value too high, this attenuation becomes more extreme, and our values of S becomes lower, and really we're measuring this signal S in the presence of random noise which doesn't go away, and so our signal to noise ratio drops. So if you put B too high, we lose sensitivity, we have too much noise. You set B too low, we don't have much sensitivity to diffusion, so we need kind of a mid-range value. That's why B times D about equal to 1 is around a good choice range. Now we're going to calculate the value of B based on a bunch of different measurements of S, given different D values. Okay, so this is our equation here. We're going to turn it around. We take the natural log of both sides, so we can more easily solve for D. Okay. Again, we're going to measure S for each voxel. We set B, calculate S0 and D. We have to do this. We have to take measurements at a bunch of different values of B, not just strength of the gradient, but also directions of B. Okay. So we can actually model the diffusion a bunch of different ways. The diffusion D is not a single value, right? I already mentioned we can measure the diffusion in different directions. There's nothing requiring that the diffusion is the same in every direction. Of course, we're going to use this when we're looking at tractography later on. The diffusion across white matter tracks appears to be slower than along white matter tracks because the water can't diffuse as far without hitting a tissue boundary, a cell membrane, and its movement gets slowed down or stopped. So the diffusion across white matter looks slower than along white matter just because it can't move as far. And so we have to allow for the fact that the diffusion is different in different directions. So we can describe it a number of different ways. Probably the simplest way is to model as a 3D tensor. Tensor is like a 3D vector that can vary with position and direction. And we can describe it as the equation at the bottom here, where our B times D, really we have to account for our different directions, X, Y, Z. Of course, the diffusion can be in any direction, but this is general enough. It describes the diffusion in 3D. We can express it a bunch of different ways, but what it comes down to is we have 6 unique values of diffusion. The principal directions along x, y, z, and then the cross terms x, y, x, z, and y, z. When you multiply b times d, we end up with this sum of, in principle, with this model, 6 different terms. Okay, so we're going to need at least 6 different measures, ideally in different directions, to work out these different diffusion values, dxx, dyyy, dzzz, dxy, dxz, dyz. And so to solve for the diffusion values for each voxel, we can write out our values like this. Again, this is for one voxel. Imagine we've acquired diffusion-weighted images a whole bunch of different times for different b values that we've chosen, different directions of b. Okay, so different values of bx, by, bz, okay, depicting the magnitude and direction of b. Now for that one voxel, we have our values across repeated acquisitions, S1, S2, S3, and our values at b equals 0. So our S0 value is actually will be the same for this voxel, hopefully, over repeated acquisitions. We can create a matrix like this with our different b values. So these are our values we've chosen for each acquisition, our directions of b. This matrix on the right is our matrix of diffusion values that we're trying to calculate. Okay, so again, here's an equation with a bunch of values we measure based on values we specify, and then our unknown values we're trying to calculate. So again, more values that we measure gives us higher accuracy. We need a minimum of 6 to be able to solve this equation, because we have 6 values of diffusion coefficients here that we're solving for. The more values you have, the better. The more values give you higher accuracy. To a limit. There's a lot of debate as if the time it takes to acquire more data is worth it, given that people tend to move. So there's a balance where it becomes unreasonable to acquire more directions. Sometimes it is argued it's better to acquire just 6 values, but maybe acquire each one twice and do signal averaging to get a higher signal-to-noise ratio in each individual measure. There's a lot of debate about it. Often people will acquire, say, 20 or 30 different diffusion directions to get good accuracy. That's a topic for another discussion. But again, we have to do this repeatedly with different b values, and now we do this for each voxel. We can rewrite this equation. Let's call this S sub m, call this matrix B sub m and d, and then it's a matrix math equation. We just solve for d. So now we can calculate our values, dxx, dyyy, dzzz, dxy, dxz, dyz. And from that we can create our diffusion tensor for each voxel. And so finally we have our diffusion tensor for each voxel. Here I'm showing just one example of what the numbers could possibly look like. From this diffusion tensor matrix we can also calculate the eigenvectors and eigenvalues. These are meaning characteristic values. These are really the principal directions of diffusion. We can find which is the direction that has the largest diffusion and what is the diffusion along the directions orthogonal to both of those. So we can describe the diffusion tensor field as an ellipsoid, and in a way describe this diffusion in different directions along our 3 axes. Again, this is one choice of model, so we're assuming this kind of simple ellipsoidal model is a correct one. There's many choices we could use, but it does a good job of describing in general the diffusion average over our voxel, right? It's the sum of a lot of signal from our voxel, and we're looking at the average diffusion over all those environments that are inside that voxel. So it's a representation of the diffusion in there. So these diffusion values we get for each voxel give us important physiological information actually. They tell us about the water environment in the tissues, which tells us about the structure at the cellular level within the tissue, and tells us about the rates of diffusion and directions of diffusion. So we can gain a lot of physiological and anatomical information just from these diffusion tensor values, and we can create images like this that show us a lot of structural detail. Now we can take that diffusion at each voxel and look at the continuity from voxel to voxel. This is how we can piece together the fiber tracks, knowing that the diffusion is greatest along the direction of large fiber bundles. Again, because diffusion is more restricted across, say, white matter tracks because of the myelin, the axon structures. than along the structures, we know that the principal direction of diffusion is likely along the large white matter tracks. And so looking at continuity from one voxel to the next, we can follow the large structures. This is the principle of fiber tracking, right? So we can make complicated maps really showing quite exquisite detail of large fiber tracks. Of course, we're going to get into trouble when we start having voxels that contain a combination of different fiber directions within the same voxel, and we're only measuring an average across that voxel. And when we have different converging and diverging fibers within a voxel, and these are things we'll discuss, I think, in future topics. So I think I've covered all the basics of DTI. Of course, there's many more topics to be covered, a lot of details I didn't cover, but I think this is a good start. Goodbye.